so that we can also have it available. So try to see if your screen can be shared there. And then we can already start with the presentations. Just reminding that we asked, please, if you could keep it to 8 minutes. Maybe it would be interesting.
I can share my screen. I can't.
Okay, let me allow you then. Sorry.
Not allowed.
Yeah, no, sorry. Now I think you can go.
Yes. Can you see it?
Wait, we're gonna start. I mean, it's starting still. It hasn't already worked. Let's see. Okay. Try passing the slides there just to see if it's if it goes well.
I'm passing slides.
Yeah, are you passing? I just wanted to see if it's
yes.
Yeah, because I think we have like a little delay here or something like that. Okay. Okay, now it passed. Okay, now a literature review. Okay, well, you can go to the first one then and start the presentation. So Bruno is from the Brazilian national selection. He's from the University of São Paulo, from the Physics Institute of that university, and they participated in the national selection and everything. He's going to share now the solutions for peculiar echo. Please go ahead, Bruno. You have approximately 8 minutes. Thank you.
All right, thank you. Problem number 8, peculiar echo. The state problem is, is it passing the slides or no? I hope the delay. Yes. Okay. So and as shown in the video, investigate the phenomenon and find the necessary conditions to create it and reproduce it. So I don't know if you can hear it, but the first video is we show the of the presentation is aspects and then develop a theoretical model to be validated with the parties, and then we draw Lugman first reporting the triplet echoes from the with the Clark's diffraction model. He uses monofrequent pure wave diffraction theory to make simulations and compare with the original echo, and he found a strong dependence between the incident sound of the clap and the echo generated, but he only does a qualitative comparison between those two. Also, there is Lugman's convolution scattering model, which is more precise and assume that an array of scatters in the corners. He also compares the generated echo with his simulations in a qualitative way. So from the waveform, we can clearly see two distinct regimes. The first one here is this big pressure pulse is from the instant clap, and then after some time you receive the echo. So from the spectrogram, we also see the same thing, but there is a very interesting phenomenon, which is the appearance of these graded lines, which we suppose our hypothesis is that this is due to constructive interference, and we'll see if this is true or not. All right. So from the spectrogram, we can also define 3 main events, which is the duration of the hand clap here, which is very easy to measure, delta T clap, and then the start of the arriving of the echo, TA, and then the end of the echo at TB. So we are given the duration of the clap, which is about 0.01 seconds, and the dimensions of the staircase we can also take for granted, and the speed of sound. But from the recordings, we have no information about the horizontal distance to the pyramid and the height of the person. We assume that both the camera, both the microphone and the clap, they are at the same position in this coordinate system, and we assign vectors to each corner of this staircase with this relation. I mean, k is the number of the steps, and they run from 1 to 91 because there are 91 steps. We also define delta tk, which is the time it takes to the sound to arrive at the microphone, leaving the kth step. So there's a factor 2 here because it's 2 ways, right? For going and then to returning. And recall that the position of the corners of the steps in the way we have defined them are a function of height and of the height of a person and the horizontal distance. And we find two relations for it based on the two main events. And because like when the echo arrives, the first sound that arrives in time TA is coming from the first step, which is for the closest one. And then the end of the echo, the sound that in the end of the echo comes from the last step. So delta T 91. All right, so, but from the spectrogram, we don't have those values exactly. So we assign some uncertainties. There's a time range to each of those main time events. And we can solve this expression here for TA and TB. We can solve for the horizontal distance, and we'll find one coming from the first relation, TA, and the other one for TB. We can now see how does it change for different heights. So for heights from for h from 1.5 meters to 2 meters, it doesn't change very much. So it's basically horizontal line, and we can just take because of this, we can just take the height to be the average height of Mexican person, so 1.72 meters. So we calculate the two distances, take the average, and find that the horizontal distance is about 31 meters. And we also estimate the error, which is about no more than two steps. All right, the model is very simple. It's based on Huygens-Fresnel principle. So each corner will be once the clap, the sound of the clap hit each of the corners, they will be new sources of spherical wavelets, and they can interfere, but and they will interfere whenever the difference in time for the arrival of the sound that comes from each step is smaller than the duration of a clap. So this is the interference condition that we are considering, and it's better explained here. This interference condition. So whenever the time it takes to arrive at the microphone from two different of sounds from two different steps is larger than the duration of a clap, they will not interfere. We can do the same thing to each two pairs of the steps, and so assuming that in the cases that they will interfere, there will be a constructive interference whenever the difference in acoustic path is an integer multiple of a wavelength. So this is the expression for the difference in acoustic path. So it's just the magnitude of the distance from these two steps, and M stands for the number of modes. So once we solve for the wavelength, we find this expression, and we can invert this expression. To write in terms of the frequency and time instead of wavelength and position. So we do that because with this we can compare with our spectrogram of the recording, and but if you plot this expression, making that inversion, we find that the agreement is very well and explains that indeed that graded lines in the spectrum is due to constructive interference. So just draw some conclusions, and recap the presentation, we make a literature review, we provide a qualitative explanation, we make very clear assumptions to our model, and we take the hypothesis that the graded lines are from constructive interference. We build a model using constructive interference and show that this explains the spectrum regarding the interference condition that we also find. So thank you very much for your attention, and I'm open for questions.
Yeah, I forget I have the microphone. I don't have to keep screaming. So thank you so much, Bruno. I think we're gonna like maybe skip the questions. Does anyone have any pressing, like extremely important questions they want to make, or are you fine? Because we're a little bit behind schedule and a little bit, I mean, an hour. So it would be nice if we moved on. So thank you so
Okay.
much, Bruno.
Thank you.
Yeah, no problem. Thank you so much, man. Joining us from Brazil. I miss Brazil. Hey, so the next person to present then is Ivan. Ivan is there, ready to present?
Yeah, I'm
Oh,
here.
nice. Yeah, you can show your presentation then. Start sharing, and
Okay.
you can also go for it. Yeah.
Can you see it? Okay. Good afternoon, everyone. My name is Ivan Prearp. I'm going to present problem number 8, peculiar echo again. I wish that I can complement the previous presentation. Saying again the problem statement, if you go to the El Castillo pyramid at Chichen Itza, and you clap in front of the staircase, you can hear a very chirped echo. So very different than expected. And the problem statement asks us to investigate the phenomenon, find the necessary conditions to create it and reproduce it. So let's start with the geometry of the problem. So you have an observer at a certain distance from the start of the stairway, and this distance is important so the clap sound and the echo sound has some time between them, so you can distinguish them, right? And then we have 91 steps at the El Castillo pyramid, and each step will be at a different distance from the observer. And in the case of Chichen Itza, we have step dimensions of the order of magnitude of a wavelength of 1 kilohertz sound, right? So the distance between the observer and each step is very important, and it rises non-linearly. And the difference in distance between each step is also important because it will give a constructive interference at the wavelength that matches this difference in distance, right? So basically what we have is a variable diffraction grid. We have a incoming wave or outgoing wave, that's the clap sound. And then at each step, we have a reflection. And these reflections have some time between them that is that makes them interfere depending on the distance between each reflection. So they have different travel times. So thinking about the constructive interference from each consecutive steps, we can arrive at a frequency that goes down with the higher the step. And for Chichen Itza, it starts at about 1.4 kilohertz and ends at about 1 kilohertz. And so to compare this with real data, we took this audio file from a site in the internet, and we've plotted a spectrogram, which is the amplitude of each frequency over time. And you can see here the clap, which is a very high amplitude for a very big range of frequencies over a very short period of time. And then we have the chirped echo a bit after that. So looking at the chirped echo, we see that there are some curves, and indeed there is a curve that it starts at about 1.5 kilohertz and stops at about 1 kilohertz. So maybe the model agrees well with the theory, but we can do a little bit better. We can do a convolution scattering model, basically thinking on that diffraction grid approach, and we can make a convolution of the clap sound with the response function from the staircase and arrive at a echo. And this response function, we can think of it as, for example, for one step, we have just a delay in the echo. The sound itself doesn't change. It just takes longer to reach us. So for the staircase, we just make a superposition of all the steps response functions. So we have a response function for the entire staircase. So just to remember how the echo sounds in Chichen Itza. And then if we take the same sound from the clap and do this convolution, right? So that's good to hear, but we can also compare visually using spectrograms. And we see the curves and they look like the same, but by plotting them at the same scale, we can draw some guide for the eyes on the experimental data, and then superimpose that on the calculated with the convolution method, right? So that also looks to agree quite well. And let's see what necessary conditions this has for the chirping. We need multiple echoes coming with different return times, and the return times must, the difference in return times must be increasing so that the frequency goes down. So if you think about it, any staircase should do. And here in Unicamp, we found 4 staircases that does, and all of them were really close to our lab. And to prove it, I bring some a audio here. Right, so you can really hear that's the same effect. And looking at the spectrogram, we can see that the echo is quite shorter because our staircase is way shorter. So the difference in time from the first echo to the last echo is way smaller than Chichen Itza. And we can test the model again using the clap sound for our staircase. So again, very short echo, but it sounds like the frequencies are going down with time. And we can do the same thing with the guide for the eyes and see that, in fact, it agrees quite well. The only thing that the theory shows an extra curve there that doesn't show on the experiment. So a question that may arise is, can we do it in a lab scale? For example, with 3 millimeter steps. And by using that quick approach of constructive interference, we can see that the frequency at which this would occur would be at 115 kilohertz. So if you did that, you wouldn't be able to hear, but maybe the bats and beluga whales close to your lab could. So it's not possible for humans. So just the concluding remarks. The only requirement for the chirped echo is a staircase-like surface, and the wavelength will be comparable to the step size. And the model basically is that the staircase will reflect the sound at different times, and will create basically a variable diffraction grid. So the echoes at different times will interfere with each other, and we can reproduce it by using a convolution scattering scheme to predict the echo. So thank you, everyone.
All right, thank you so much. Thank you so much, man. We weren't able to hear any of those. Like, I don't know if it's possible for you to try to connect the audio so that just we can hear one of those clapping.
Sure, I think I connected now.
Okay, let's see.
Okay, so that's the experimental one, just to show the right. So.
Oh, okay.
So
that was interesting. I had the.
Yeah, this one is the Chichen Itza one.
Nice. Okay, so it's very similar. Interesting.
Yeah.
Nice. Cool. Thank you so much. Thank you so much.
Thank you.
I think that people will appreciate when they're watching this afterwards, this last part, so they can actually hear how very interesting you were able to reproduce the sound of the chirp and the sound of the clap using your model. So thank you so much for the presentation. Congratulations once again.
Thank you.
And yeah, does anyone have any interesting questions? If not, we can move on to the next presenter. Thank you so much again, Ivan. Thank you. Cheers. Please feel welcome to tag along and stay there to watch the other presentations too that we're going to have here at the IPT conference. So the next person who will present is Iason Kazakis from Team Greece. If you want to connect your computer, I think it would be interesting for you to join the meeting. I'm going to ask this to all the people too, like if you're going to present, like please join the meeting so that we can record it and have it forever. So yeah, and in this case, you can even present using the, okay. I'm glad it's working out. See, because it's, the audio wasn't working, then it was, then the guy trying to reproduce the audio, now it worked. So I'm happy, you know. I don't even know what problems are going to be in the final. Does anyone know? Okay. Okay. All right, cool. I don't think we have any solutions of those in the IPT conference, I believe. So it's going to be nice. Okay. All right. You can share your screen. And the audio can be through here. You can just present like near this. No, you can use the
okay.
and then share your screen.
Okay. Entire screen
How do I choose?
or the
Share.
window.
I don't know.
Mhm.
Can you go to your?
Yes.
No, sorry.
Yes. Here. Okay.
All right.
Perfect.
If you want to appear on the camera, it's here on this computer.
Okay.
So without further ado, you have 8 minutes approximately to present.
Hello, my name is Iason Kazakis, and I will present you problem number 1, Galton board. So the problem states that using a Galton board, we can generate some kind of distributions by varying some parameters like peg size, bit format, etc. So we want to test if it's possible to achieve a distribution that does not obey the central limit theorem in an IID scenario. And we also want to examine what happens to the distribution when one makes the board to vibrate. So starting with the Galton board, you're probably familiar with the setup. This is basically it. And in order to examine it, we will use this mathematical formulation where we suppose that every obstacle in the Galton board basically is centered in a unit cell of a bigger lattice. And we're having a random walk of one step that leads to the final placement in the Galton board in the beams that create the histogram. So what we want to obtain from that is having the final vector that will give us the final histogram. So the movement in the Galton board basically follows this rule, having probability to go to the left and 1 minus that probability to go to the right in order to sum to 1. And also we will take the partition of the PDF that we're using in case we have a continuous distribution, and we will transform it to a discrete, like a vector, basically a histogram, a discrete distribution. So the difference here is that every probability in this lattice is not the same, but we can choose for every unit cell to have a different probability, where instead of having the constant probability, now we have a product, and we sum for all the possible paths up to K choose L. And in order to compare theoretical distributions with what we get, we will use 2 different tests, a Kolmogorov-Smirnov test with a p-value and the chi-squared test. Those are metrics that compare those 2. So the model that we use to change the probability for every cell, it basically takes the obstacles of the lattice and makes them to be triangles that we can twist them, we can rotate them to change the probability to fall into the middle. So through that, now we have three important angles that we want to compare: the probability to go to the angle to go to the left, the, let's call it, active angle to go to the right, and how much is rotated. Also a middle angle where basically it falls to the point of the obstacle, and it's almost the same probability for each side. And if we suppose it follows a normal distribution, the final probability can be calculated through that. Okay, and in order to do the reverse engineering, we will need also some more calculations. We can use a transport matrix from the Markovian to simulate it like it's a Markovian chain. And we can give a specific probability for every transportation in the lattice through this matrix. We will use that to do numerical simulations later on. So in order to do those, we suppose an initial state, and then after k minus 1, after k transitions, where are multiplications, we can get the final state to be vk, where all the probabilities here are sum to 1 to be a distribution. So I will skip that due to time. Also, I want to mention that there are some specific distribution called stable distribution, and they will be present in any case that we have a Galton board. I can leave that for the end. And so in order to examine whether the central limit theorem can be satisfied, distribution basically does not obey, or maybe better satisfy, the theorem in case that it has something like a fat tail, a variance or an expected value that cannot be defined, goes to infinity or something similar, usually in those kind of distributions. Though we can generalize the central limit theorem and having stable distributions where they present those problematic behaviors for the mean value and the finite variance due to the fat tails, but they will still satisfy the general central limit theorem. Okay, I will skip that also. And I will move on to some simulations we did with PyMonk and PyGame, where we simulated for this different kind of falling objects and obstacles, the movement in the lattice, and we had those kind of different distributions that we correlate them to those theoretical PDFs. So those are a few. We experimented a little bit with different shapes and sizes. And okay. And also we did a Markov chain Monte Carlo simulation and a physical simulation to simulate the vibration. And I have the questions in the appendix. So our first experimental procedure basically had a classical Galton board where we can change the pegs, the board, and all the falling objects we used to pretty much see what parameters actually play the most important role in the process. Those are a few examples for two different kind of falling objects. And we want also a second experimental procedure in order to examine the vibration and the oscillation. So that's why, and also to test our angle model, as we call it, the theoretical model, by having the obstacles to be rotatable. So this is how it works. We have an electric motor that makes the thing to oscillate, the board to oscillate, and we can also rotate the angles quite easily of the obstacles. And so what we got were some comparisons. This is, for instance, a Gaussian and Cauchy distribution. So they look quite alike, but those kind of distributions, the one actually satisfies the central limit theorem, of course. The other one doesn't because it has a fat tail. And as you can see, we somehow try to correlate it more with the Cauchy rather than the Gaussian. Also, we had an almost constant distribution. A Maxwell-Boltzmann Gaussian somehow convolution. We had an obstacle that split the two things, the two falling objects into two parts, and they gave them a speed. So it was something like an ideal gas velocity distribution. the log normal distribution. And also we tested what happens when we vibrate the board, and we noticed that variance increases. So for low RPMs, we still have a Gaussian. Here we have a constant probability in each cell. And when we increase the vibration, we increase the RPMs of the electrical motor, we saw that it tends to go to the constant distribution. And so, yes. And those are our results where we compare here the p-value. We suppose that the significance levels of the p-value is said to be at 0.05, where that means that everything below that is satisfying enough to keep it. So our conclusions are that our theoretical model, the computational approaches and the experiments are quite well correlated. And we can actually create different distributions that do not necessarily satisfy the central limit theorem, but they can satisfy the generalization of it. And we examined what happens mostly with the variance of distribution, a Gaussian distribution, when we make the board to vibrate. So we also try to develop a machine learning model to do the reverse engineering and to find the probability for the entire lattice, and we want to keep working on it. So thank you very much, and that's it.
All right, congratulations, Iason. Does anyone have any quick questions or something like that? You can also talk to, okay, Vova has one, okay.
Generalization of the central
You can start sharing. Oh.
There are some distributions that do not satisfy the central limit theorem, like Levi, Cauchy, or Landau. Yes, but because they have fat tails, but in its generalizations, those distributions are called stable distributions, A-stable, alpha stable, in fact, and they do satisfy the generalization of it only. Those are used a lot to simulate those distributions that do not specifically satisfy those theorems.
All right, okay, I think we can move on. I'm sorry, but wait, it's just, we need to run a little bit with the time. So thank you so much. Let's thank Iason once again. Thank you. So now we're gonna have a presentation by Penelope from Team Canada. She's gonna be presenting problem alcohol sound check.
Good. Hello, it works? Okay. Okay, hello everyone. I'm Penelope Pouli from Team Canada, and I'll be presenting problem number 4. So I can change from here the slides. Okay, so I'll be presenting problem number 4. So practically this problem talks about a difference in the sound when hitting a bottle before and after turning it upside down, where the state of the liquid has changed. So we want to investigate how this difference in the sound is produced, why is it produced, and why we call it a damping effect, and maybe what liquids will maintain this damping effect further, will maintain this change in the sound further. So from this observation and from the question, we thought of this experimental setup, which is just a great bottle of vodka, 2 microphones which are fixed so we don't move them and they don't alterate how they receive the sound, a metal chopstick, and a rotational motor. So this motor there, it's a servo motor, which is connected to an Arduino machine. So we connect, control the intensity that we hit the bottle. So we don't alterate the mechanical energy that is being added to the system for each trial. So our research plan and hypothesis was to try to fill the bottle with different liquid and gas ratios to investigate the bubble distribution inside. Because when a bottle is full, maybe no bubbles will form or very little bubbles will form, and try different liquid and gas variations. And then we will try the carbonation factor, carbonated liquids like sparkling water or soda or beer with alcohol. So we actually saw from here that when we turn the bottle and bubbles form, there's actually a difference in the intensity of the sound. That's the main difference that we noticed. So when you see at the spectrograms on the left, which are directly taken from the software Audacity, which collects the sound, we see that the intensity of the sound, which is in decibels over there, remains the same. But after, when we reduce a little bit of the volume inside the bottle and actually bubbles start to form, and it's not fully filled with liquid, we see that there's a vast difference between the intensity from minus 16.9 to minus 40. So we also want to investigate why this happens and why the frequency changes as well. So we will try the different liquids that are displayed there, ethanol, and then diluted ethanol with water, and the plain water, glycerol, a mixture of glycerol and water, and finally beer, to investigate how alcoholic carbonated liquids will respond to this difference in the state of the liquid. So we'll get right into the hypothesis that we have, which is that when we heat the bottle and we add this mechanical energy to the system, these vibrations that the particles will make will cause the pressure variations that we receive as sound. So this sound wave that we send inside the bottle will meet the bubbles. So if the sound wave of some frequency f corresponds to the natural frequency that the bubbles would oscillate, we will have a driven oscillation that we caused from heating the bottle. Now, this driven oscillation will cause the bubbles to pulsate at their natural frequency, will cause them to change the volume while they're getting damped from the liquid around them. So now we are talking about a driven damped oscillation, and we will proceed on how we can actually measure the frequency that the bubbles will resonate at. So from here, the mean end resonance, which is a formula that's employed for bubbles inside liquids, and it's totally radius dependent, because where you can see here, it's actually 1 over 2 pi a, where a is the radius of the bubble, and there it's a constant that depends on the bulk modulus of the gas enclosed in the bubble and the density of the liquid surrounding the bubble. So F will be inversely proportional to the radius of the bubble. So now what we need to do is see what different constants the liquids have and how can we determine a radius range in order to determine a frequency range for our sound. And that's what we did. We tested liquids for different densities, and we have here a plot which presents the densities for different liquids from decreasing to increasing density. And we had some fancy mixtures there with water and glycerol that will be presented later. And now the only thing left, now that we've determined the constant, is the radius. So we will use a method which is called the Son diameter method. And it is this one actually. So when you have a bottle which is filled with bubbles, we can actually take pictures, take videos, and actually calculate the exact radius of the bubbles during their motion from the bottom to the top of the bottle. However, this might need image processing and laser diffraction, which we did not do because we didn't have the budget. So we actually used some data that we found, and they're interpreted through this method, the Soter mean diameter method, which is a method that they can actually calculate the mean diameter of some spherical particles inside a liquid by taking the summation of the volume and the surface area of those small spherical particles inside a big fraction of spherical particles. And from there, we get a distribution, we get like the mean radius of what we expect to see of bubbles inside specific liquids, depending on their properties, of course. So now, from our liquids that we tested, we have a graph which corresponds to the liquids and the bubble size that we expect to see. So remember here that the the resonance theory that I presented before, which relates the radius and the frequency, it actually talks about spherical bubbles. So that's why we have limited our radius for the criterion that the bubbles are spherical and they are not deformed as they go up and the surface tension increases. So from this, we actually get the frequency range, since we have the radius range and they're totally dependent to each other. So now that we have the frequency range, we actually wanted to record the sound that we hear when hitting the bottle and seeing if it actually corresponds to the range that we have. So up left, we have the frequency of the sound wave that's emitted when we hit the bottle before we turn it upside down. And on the right, it's actually the sound that we hear when we turn it upside down and the motor hits it again, where the state of the liquid has changed and there are many bubbles inside. So before, we see that after actually the frequency is inside this expected Minard range that we wanted to see if the bubble actually pulsates at its natural frequency and it's doing a driven oscillation. Factor of each liquid that we tested.
Okay, I think maybe
Good.
now it's better.
Now it's well, a way to quantify the damping factor of each liquid is to actually calculate the quality factor of a damped oscillation. So the bubbles are performing this damped oscillation. There is a very good way to quantify how damped the oscillation is for each liquid. So we actually collected the frequency and the intensity of the sound, and we performed this Lorentzian fit, which will result in the Q factor. This Q factor will give us how many oscillation will a bubble be able to perform before it gets completely damped by the liquid around us, maybe from the pressure factor or the viscosity factor. Here, it's the resonance curve of a bubble in ethanol, which was the main liquid that we tested. And here it's the Lorentzian fit that we put for our data that we extracted from Audacity. So now we want to actually interpret what this Q factor means and what this damping factor means for the liquid that we're using. Here, I have collected a table with all the Q factors, the quality factors, how fast an oscillation is getting damped for the liquids that we tested. And we can see that from glycerol to water and ethanol mixture, we have an increasing Q factor. We expect more oscillations. When you see an increasing Q factor, there's more time for bubbles to oscillate before they completely get damped from the liquid around them. So we have a relation. We expect what to see for the sound depending on the viscosity of the liquid and the density of the liquid. And actually, we can also estimate the time that this difference in the sound will be maintained. As long as the bubbles oscillate and they're getting damped, we can actually calculate that it's going to be 3 seconds that this difference in the sound is going to be actually noticeable from us. So, continuing, we have this spectrogram right here, which actually demonstrates the sound before we hit the bottle, before the bubbles are formed, and after the bubbles are formed. So I hope this is the before the bubbles are formed. It's just the sound of a bottle, which is emitted just by hitting the glass bottle where the liquid is at a stable state. And here you can hear a sound that is a lot flatter, a smaller intensity, and most probably for most liquids that we tried, a larger frequency. the frequency where the bubbles oscillate at. So continuing, this was a very important step because we actually, by extracting our experimental data and putting them into our oscillation, our damped oscillation equation, we can actually calculate the damping factor of each liquid. So if we can calculate the damping factor for each liquid, we can actually estimate the amplitude of the sound that will be produced by the bubbles. So we wanted to see through this simulation if the amplitude of the sound that will be produced and the intensity will actually correspond to what we hear when we hit the bottle. And actually here, there's a spectrogram of the frequency over time where the more intense it is, it's a higher amplitude, a higher intensity, and the sound becomes louder. And for different damping factors, you will see that from an increasing damping factor to decreasing one, the sound becomes louder as the damping factor decreases because the oscillation lasts for longer. So that is the sound for different damping factors depending on the liquids that we tried. So finally, for the last part of the question, which is why this damping effect does not actually work for alcoholic beverages, is that from the testings that we did with beer, is that the beer, both before and after, it doesn't have a stable state. For water, ethanol, and other liquids, we actually had a stable state before, and then we turned the bottle upside down and bubbles form. So there was this difference in the state. With beers and the carbonation factor inside, and this layer of foam at the top, we cannot actually apply the Minard resonance theorem that we were applying for the previous liquids, because as you can see from the spectrograms, there is not a big difference between the frequencies and the intensity of the sound, since this layer of foam at the top actually acts as an acoustic insulator that insulates the sound, and there's this low value of amplitude from -45 to -48 decibels. This was also tested and verified for the mixture of ethanol and water. So a smaller density, it was diluted. And finally, for sparkling water. So all of our liquids that we tested actually correspond to this theory, and the expected frequency range from the radius range was verified. So here are some sources of error that we could have eliminated, such as injecting the bubbles and not just turning the bottle around. So we have more control of the growth of the bubbles and how they collapse. And also this collapse will also cause some variations in the sound. Maybe the sound that we hear is not solely determined from the volume oscillation, pulsation of the bubble. Maybe it's their creation, collapse, and the source of the bubbles. And finally, the conclusions that we have is that when there's this presence of bubbles inside the bottle, the sound that we hear is caused from the bubble oscillation, and that the frequency will correspond directly to the size of the bubbles. Now, there is no a big change. There is a small change, but not that noticeable for carbonated drinks, since there's this very thick layer of foam at the top, which increases the surface tension and causes these drinks to emit a sound at the lower range of intensity, since they act as insulators. And finally, the damping effect lasts longer for liquids that will maintain the oscillations longer, which means for liquids that have a lower damping factor. So that was it. I hope you liked it.
All right. Do we have any very pressing questions or no? Or because we went a little bit over 8 minutes, like 5 minutes. It's fine. All right, then let's check. Who's the next presenter? Is let's see here. I have to check on the schedule again. Let's see. It's the Polish version of my name, Mateusz. Okay. If you could join the Zoom meeting and everything, and you can already share your screen. Thank you so much for the people who are watching us online that told me that the audio was not being heard, because we fixed it. So thank you. It's room 1. Oh, yeah. Right. And then you can also share your screen. You don't have to share the audio. The audio is going to go through
Yes.
the
Okay.
share screen. You can also share audio if you need, but whatever.
I don't need
No? Okay. then just share the screen.
share the screen. Okay.
All right.
Mm.
Cool. We have 8 minutes. Go over time a little bit. 5 minutes. Go ahead.
Hello, everyone. On behalf of the Poland Kraków team, we want to present our version of solution for problem number 6, salty shapes. It was already presented 4 times during selective fights, and we had the pleasure to compete in 3 of these fights. So we have seen a lot of solutions, and when we have these problem descriptions, most of them have answered the first, one answered the second, and 2 answered the 4th question. But we think that none of them had actually completely solved the problem, the question number 3. To understand this question, we need to know how salty shapes are produced. So before we thought that they are created by some stresses in crust, like when the ground is dry, it creates some similar shapes. Also, it was thought that that salt, when it's wet, it creates a hydrate and it's expanding. But in 2023, there was a paper by Jan Lasser et al. That showed us what is the real solution to this problem.
There are upstream flow of water, and when it reaches the top part, evaporating causes it to increase the density. And there are form umbrellas of this flow. And when 2 umbrellas meet, then salt ridge is on the connection. Here we see points are the middle of umbrella, and then umbrella expands. And when it touches the others, it creates straight line.
And now we know that this kind of straight lines in the middle of 2 points create a pattern known as Voronoi mesh. And we checked if shapes that was seen on one of the photos are can be properly reproduced using Voronoi mesh. So here is the photo. Here is and below we see photo that is corrected due to perspective, because I don't know why, but there are literally no photos of salty shapes from above. All of them have some kind of perspective. And here are the results. So you can see that it's not that good, because we can see that while some shapes are reproduced good, but some shapes are. Is there something to point? Like some shapes are too big, and some shapes are too small. So we proposed some kind of variation of Voronoi shapes that we called a Swiss cheese Voronoi pattern. So just like in previous slide, we have seen that all the points has the same radius. But we know that in Swiss cheese, the eyes aren't the same. They have different radiuses. So we proposed a variation of Voronoi mesh with waves. So we can, so if a shape is in our simulation is too big, we can shrink them, and if it's too big, we can inflate them. So here is the result, and you can see that it is much better than the previous result.
Okay, we can see that not all the ridges are visible. Some of them are only half created, or even some percent. But it is also included in our model. Also, these shapes aren't all convex. Some of them are concave, and also using weights in the Voronoi diagram, we can achieve that. Instead of straight line, achieving arc, part of arc.
I want to add that in the previous slide, we can see that if the wave is too small, which in reality means the flow is too small, that the ridge is not created. And what is more, we proposed an experimental setup to check our theory.
So basically, we put pipes in the certain spots on the bottom of box, and by modulating the flow of water in this point, we can modulate the shape that we want to create.
And that's all.
Thank you so much for the presentation. I really like the umbrellas. Does anyone have any questions they would like to ask? Very briefly, Wolfgang, please. Thank you.
Thank you for presentation. What are weights in your Voronoi cells? Do they have physical meaning, like average permeability in the region of the ridge forming? Yeah, but I ask about physical reasons. Why are the weights different? Is it because of different permeability, or there are some other reasons? Okay, thanks.
All right, cool. Thank you so much again, Mateusz. Yeah, now we move on to the next presentation. I believe from Team Iran, we have Amin Reza online. Hello.
Hello, how are you?
Hi.
Can you hear me?
Yes, we can hear you.
Hi.
Nice, yeah. You can start your presentations, and welcome to the IPT. It's nice to see the team from Iran participating. And yeah, you can go ahead, share your screen, and start your presentation. Thank you. Opa.
Can you see my screen?
Yes, yeah, it's working. Don't worry. Try sharing it, like just click or press F5. Yeah, now it's great. Yes. Thank you. Now it's working.
Okay. Good afternoon, everyone. My name is Amin Reza Mahmoudi, and I'm a member of Iranian team in this competition. Today lecture will delve into the fascinating world of acoustic and Asian structure. Uh, excuse me, my screen move or not?
Yeah, you haven't changed the
change.
slide here. Yeah, it appears it didn't change the slide.
The Great Pyramid of Chichen Itza hold an acoustical marvel, the creeping echo. This intriguing phenomenon occurs when a clap or similar sharp sound resonate against the pyramid steps instead of a topical echo. A series of chirping emerge, reminiscent of a Quetzalcoatl call. This unique echo piqued the interest of researchers who sought to understand how the pyramid design shaped the sound. Through the miraculous simulation involved diffraction, they discovered the fascinating revelation. The creeping effect isn't influenced by the initial clap pitch. Instead, its horizon solely from the intricate geometric configuration of the pyramid itself. Two prominent models attempt the explanation this capitating acoustic interaction. Lotman torsional scattering model. This model I'm sorry, I think no change.
Can you hear us?
Yes, I think my PowerPoint no change page.
Yeah. On which
this-
side are you right now for you?
And okay.
You are on
I
intro.
test it on next page. Can you see next page?
Yes, we're seeing. We're slide 5 now.
And next,
So are you with us? Yes. Are you presenting right
I
now?
change.
You're on
yes, I
slide
change
5.
Okay, continue.
You're on slide 5.
Okay.
If you
Now-
try to go to slide 6 like this, can you try? Can you go to slide 6?
Yes, I tried. Are you? Can you see? Yes.
There's an option when you try to control like his screen. You know what I mean? You can. No, it's not. Yeah, try it. Try to continue from there then.
Okay. Lopman torsional scattering model. Can I continue?
Yeah, try to see. Right now it shows the introduction to peculiar
This
echo.
model, despite okay. No. I'm sorry, I'm go to next page, but still. Lobman torsion scattering model. This model depicts the collapse echo process as a linear and unchanging system. However, it's predict contradicting the observed phenomena. It suggests the echo frequency depends on the initial sound random categorized, which isn't the case with the creeping echo. Tekler diffraction model. This model offers a more convenience explanation. It's proposed that third step of the pyramid function as a diffraction grating, similar to how the prism separates light. The step selectivity scatters sound wave based on their wavelength. This selectivity scattering leads to a specific pattern of echoes reaching the listener ear and slightly different times. Two methodology. Diffraction simulation, understanding the echo formation. Diffraction explain. Diffraction is a wave phenomenon where wave, like a sound or light, bend or separate out as they encounter obstacle or pass through the narrow opening. Imagine water wave separating out after passing through a gap between rocks. Pyramid as a diffraction grating. The third step of the grating pyramid acts like the gaining diffraction grating for a sound wave, similar to how prism separate light into its continued color. The step selectivity scatter sound wave based on their wavelength. And simulation of the echo using the sophisticated computer simulation research can model the interaction between the sound wave and the pyramid step. I'm sorry.
I don't know.
Using sophisticated computer simulation, researcher can model the interaction between a sound wave and the pyramid step. This simulation take into account the geometry of a step, size, spacing, and overall shaping, the properties of sound wave frequency and wavelength. I'm sorry, Matthew. I think delay with change my slide. Matching creep. The simulation revealed that a specific way sound wave diffract from the step create a pattern of echo reaching the listener at a slightly different time. Our brain perceive this rapid variation in arrival time and the change in the pitch, resulting in the categorized creeping effect. The simulation revealed that a specific wave sound wave different from the step, creating a pattern of echo by reaching the listener ear and slightly different time. Power of this simulation, diffraction simulation offer a valuable tool for understanding the creeping echo because they allow the researcher to analyze complex interaction between the sound and the pyramid structure without the physically altering the humans. And the next section explains about the Lobman torsion scattering model. The Lobman torsional accelerator model proposed by D.M. Lopman offered a simplified approach to explain the echo phenomenon at the Great Pyramid of Chichen Itza. Core idea for this model, the model depicts the interaction between initial sound and the resulting echo as a linear system. This means it assumes a constant and unchanging relationship between that two. Imagine a simple spring system. The force applied such a collapse and determined for a force exert branch such a echo in the predictable way. And here's why the Lopman model struggle frequency dependence. The model predict the echo frequency should depend on the random distribution of a frequency within the initial sound. It's simpler term. The pitch of the echo should change dependent on how high or low the initial collapse sound. Reality and prediction. What?
No, I was gonna ask, do you still have a lot to present? Because I hear like he came forward and came back for some slides. I don't know which part are you in now? And it's been like 14 minutes.
I am
14.
in analysis of result and contradiction.
Yeah, now
I'm
it's
sorry.
yeah, I don't know. You can try a little bit more, then and then let's see. You have 2 more minutes to finish. Then, if possible, go ahead. Sorry.
Okay. Okay. I think the PowerPoint is broken and continue. And declared diffraction model. In this model, speak about the frequency independence and the rule of the pyramid geometry. The declared diffraction model provides a powerful conceptual framework for understanding the creeping echo. And then how the diffraction shaped the creeping echo. Path length variation and the time delay. The path length traveled by a diffraction wave will differ slightly. Some wave made the travel more bent more the travel longer, and consistency with the observer echo behavior and the correlation of the diffraction principle and simulation and modeling. In the conclusion of Chichen Itza isn't just a marvel of a Mayan architecture, it's a testament to their potential understanding of acoustic, the captivating creeping echo phenomena adds another layer to its historical significance. Our exploration delved into the mystery behind the echo, examining 2K model and the Lopman torsional accelerator model and the declared diffraction model. The Lopman model offered a basic explanation but failed to capture the nonsense of the creeping echo. Scientifically sound explanation for the captivating acoustic phenomena by considering how the sound wave interacting with the interacting structure of the pyramid. The Dickler model effectively explained the frequency independence and the role of the pyramid design in the creating the categorized creeping effect. And finish. Thank you for attention, and my PowerPoint don't work good, I think. I can hear you. I can't hear you.
Sorry, now there's sound. Okay, cool. So thank you so much again. Hey, we have now the next presenter is Lucas Heck from the Federal University of ABC. It's where I have done my undergrad too, so I'm very happy to see his presentations too. So Lucas, if you would like to share your screen, we can start your presentation as well. Thank you. Yeah, we cannot hear you, huh? So maybe turn on your microphone there. Yeah, we still cannot hear you. What you're, is it working there? Like, can you make sure I can hear you here? Let me just try to see. Yeah, we still cannot hear you, so just make sure everything is going well. Let's see. Yeah, see, I can't see the shiny thing, the green thing when you say something. So I think it's just a problem with his microphone.
Okay, now you can hear me, maybe?
Ah, yes. We're just gonna decrease here the volume a little bit.
Great, okay, so can you also see my screen? I cannot see.
Yeah, no, we can see the screen, don't worry. Yeah, now if you
Okay.
wanna put it on presenter mode, then it's gonna go. And then
Can
you
you
can
hear
start
the
presenting.
sound it's making as well?
No, you have to also share the sound if you wish us to hear the sound. You have to click on share screen and share sound as well when you click. Yeah, when you click to share the screen.
All right. I think it's working now. I'll assume it is. Okay. I'm ready to begin. Hello, everyone. My name is Lucas, and I'll be presenting problem number 4, alcohol sound check. So just a quick review of the problem statement. Some distillers in Brazil praise their product's quality by the distinct sound it makes when the bottle is hit after being quickly turned upside down. We have to investigate the phenomenon, explain why the effect doesn't work with alcoholic carbonated drinks, and explain what other liquids will maintain this damping effect for longer. So what is this effect, right? This is a video they made available for us. A very sharp, glassy sound as you expect, and then a dull sound. What's going on there? So beginning with the investigation of the phenomenon, I'll be very straight with you. The effect happens because of bubbles, and I'll show you what I mean by that. So I'm hitting the bottle here, and I'll blow bubbles, and you hear the effect. Great. So this is just to show the mechanism in which bubbles are inserted into the liquid whenever you turn it upside down. What you're doing there is that you're introducing this air pocket that's on the top of the liquid inside of the liquid. And that's how the bubbles are introduced to the liquid. This just show how turning the bottle upside down creates bubbles there, right? So moving to the first question, why does the effect not work with alcoholic carbonated drinks? I'll be very straight with you again. And the reason is because it actually does work. So this is a Corona beer, an alcoholic carbonated drink. You can hear glassy sound. We turn it upside down and you can hear a dull sound. So the effect actually works with alcoholic carbonated drinks. Moving on to the last question, what other liquids will maintain this damping effect for longer? And the answer is, let's not be too hasty about this presentation, okay? So let's go over to the literature. This is the birth of the problem, as far as I can tell. It's called The Damping of Sound by Frothy Liquids by Dr. Arnav Malik. He was a student of Lord Rayleigh's, by the way, interesting fact. And he states that the fact that a tumbler containing a frosted liquid gives a dull sound when struck is familiar to everyone, which is a very bold statement, if you ask me. But I cannot find that any explanation of the rapid damping of the vibrations, which is indicated by the character of the sound, has been published. This matches almost perfectly what we're saying, what we're seeing here. And he's also acknowledging that this might be the first paper ever on this. And so his explanations on the paper are that the bubbles receive most of the pressure waves, and this makes them oscillate back and forth. This oscillation, of course, takes energy away from the waves because of the viscosity of the liquid, and this reduces their amplitude. And so he comes up with this equation that relates the work dissipated per vibration to the total energy in the liquid. And these are the important parameters which sheds light to the important parameters to our phenomenon, which is the kinematic viscosity, the ratio between the liquid viscosity and total density, the period of oscillation, the bubble radius, and there's a quantity that relates to the void fraction, which is how much air bubbles to how much liquid there is inside of the bottle. And so this is just show that the literature is very vast, actually. We can see there's still papers being published on it. What Dr. Arnav Malik described was a monopole resonance in the bubbles, and we have papers talking about multiple resonance in bubbles, and also sound scattering, acoustic scattering, which is also a very important part of why this effect happens, not only damping, but also acoustic scattering. So let's talk about the models we use. So this is a tumbler containing bubbles inside, okay? So we have the cylinder with radius A with height H, and what we're doing here is we're making a distribution of bubbles inside of it. So initially, it can be thought as a uniform distribution in bubble sizes, in bubble diameters. And so there will be K different sizes of bubbles and different bubbles of each size, and a big N total number of bubbles. And so what we know is that for low Reynolds numbers, we can use Stokes' equation to talk about how fast a given bubble of air will rise in a certain liquid. This is a quick animation just to show that this equation seems like something that actually works in real life, and it is. It's a testable equation. Okay, so we can use this to model how the volume of air inside of the liquid will change over time. We know that this is a velocity that a certain bubble with a certain diameter will raise with time, and so we can talk about a layer of bubbles with a certain diameter, or at least in the range of the certain diameter. And so this is how this volume changes with time, of one layer of diameters. So this is a graph to show how this changes with time. Of course, whenever the bubble reaches the top of the liquid, it bursts, and so there's no volume anymore. And if we sum all of these lines together, we can get a profile to how the total volume of air changes inside the liquid over time. The H function there is the Heaviside theta function. So this is for a uniform distribution in bubbles, and this is for a Gaussian distribution in bubbles, just so that the profile of the curve is about the same. And so showing them side to side. And let's talk about the experiments we made. So this was our experimental apparatus. We had a light box to shed light into the bubbles, so we can clearly see the bubbles, so we can have a visual measurement of the phenomenon. And so we have a metal washer there heating the glass bottle to generate the sound, and also a camera to hear the sound. And this is a picture of the setup, and this is the kind of videos we can make with the setup. We can see what's happening, and we can hear what's happening at the same time, and so we can correlate the two measurements, which is great. So this is the sound measurements we can make with this. I don't know if this is on top, I guess. I hope not, but okay. So before shaking, this is a profile of the spectrogram of the sound. And you can see there are a lot of high frequencies there, which are lost after shaking the bottle, which is precisely what we hear, right? A dull sound, a less pitchless sound. And so here is a long time spectrogram of the effect happening. You can see that slowly the frequencies return, and you can see that the higher frequencies take longer to return, which has a relationship with the Rayleigh's diffraction also, which is quite interesting. But then you can see this animated picture of each period of sound in which the oscillation, the heating happens. And so you can see that in the beginning, the higher frequencies are damped and they slowly return. This is for soybean oil, which is a little bit thick. This is for glycerin, which is very thick, or meaning very high kinematic viscosity. Before shaking, you can see there are a lot of frequencies there, high frequencies, and they take longer to return in glycerin. And so this is for water as well, just for completion. And water takes very little time to return to its current state. So, and this is an idea for analysis to measure the bubble distribution inside of the liquid over time. So something you can see is that because of light diffraction, light scattering actually, you can, it's darker whenever there's more bubbles and it's lighter when the bubbles are going away. So maybe we can correlate that with the amount of bubbles inside of the liquid. And this is how I did it. I took an average of the luminosity inside of a given region over time, and this is color inverted. So I could get this profile of luminosity over time. And this profile actually has a nice curve to it. And this nice curve is also related to the nice curves we had from the theoretical model. So in conclusion, we found out that the most relevant parameters to the effect are the void fraction, which is the ratio between the volume of air bubbles and the volume of liquid, the kinematic viscosity. The higher the kinematic viscosity, the longer lasting is the effect. And so we can understand the underlying physics through a simplified model of the system. We can devise a method to determine the amount of bubbles in liquid, measuring how long the effect will last. And so we have investigated the phenomenon, show that it works with alcoholic carbonated drinks, and show the relevant parameters to determine which liquids will maintain this damping effect for longer. Thank you.
Thank you, Luca.
Thank you.
Do we have a question in the room? I think we have time for a question.
Thank you very much. This presentation. There is a question, what relates the sound to the quality of alcohol? Did you finally found the answer to this question?
Okay, this is a great question. I had to put it in the miscellaneous, and the actual reason why there's a relationship between the quality of alcohol and the sound is because for cachaça specifically, I don't know which other spirits, but for cachaça specifically, you can correlate the viscosity of cachaça to the quality of it, because the longer it stays in the wooden barrel, the more it takes glycerin, which rises the viscosity of the liquid. And so it's not about the sound, actually, it's about the viscosity, but the viscosity has a relationship with sound. And this is not...
Thank you. I understood your answer. It's interesting. So it's viscosity, but not surface tension, yeah?
Yeah.
Okay, thanks.
All right, thank you. Let's thank Luca again. Thanks for joining us.
Thank you.
Now we have Zahra. Zahra? All right. Who's going to present to us, and then so we should switch this.
happened before? Did you have a problem like this before?
No, not really.
Okay, we're gonna find a solution.
It should get to the Zoom meeting, but what happened? Did it just walk? Shutdown project? No? HDMI.
Hey, thanks, Mateusz. All right, so the Zoom. Still working? Yes, perfect. All right, I think you can. You go back, exit. I'll just change one thing. So it's in the Zoom, you're gonna have a new share. Yay, perfect. All right.
So hello everyone, I'm Zahra Hosseini, and now I'm presenting Jumpy hoop. So the problem states that given an angular momentum, a hoop with a mass attached to it may demonstrate a jumping motion, but it is rolling. Explain the phenomenon and how it depends on the relevant parameters. Is it possible to reproduce this behavior within an unbalanced distribution on a wheel? So first of all, we'll have an introduction, an initial observation of the phenomenon. So we can see when the hoop starts rolling on the ground, it will have a jumping motion. The hoop has an internal diameter and external diameter and a mass attached to it that I showed with M here. Now, the schematic view of the jumpy hoop shows that it will start rolling on the ground and after a while it will hop. Now we are going to investigate the parameters that affect this phenomenon. So we have a simulation with COMSOL, and these are the parameters that I used for the simulation. And this is the displacement diagram. It's basically the same simulation, but like in a diagram. And we can obtain diagrams from the simulation, which one is for velocity versus rotation angle. On the left, we can see that when it has an initial velocity that is 3.1, and when the hoop is starting to rolling on the ground, we can see that when increasing the rotation angle, the velocity will change, it speed up and it slowed down, and mostly that is the main reason for that is because of the mass that is attached to it. So it will have a kind of a periodic motion. Sometimes it will slow down and again, it will go up. And another diagram is energy versus time. You can see that when the kinetic energy is in the maximum amount, the potential energy would be in the minimum amount of itself. And the total energy of the system is decreasing. And that's basically because the friction force is increasing, and it will make the hoop to stop eventually, like it will roll on the ground, it will have a jump, and it will stop because of the friction force. And now we can say that here we have a schematic view of what forces are applied to the system. We know that the O is the center of the hoop, G is the center of gravity, and P stands for the particle, all the mass applied to it. It's basically the same as M, and C is the contact between the hoop and the ground. And the main force here that I'm going to talk about later is the normal force that is exerting from the ground to the hoop. And F stands for the initial force that we give to the hoop, so it will start rolling on the ground. Now, if we give a coordinate system to the G, the center of mass, that will send an Y and X, we can follow the theoretical work. So here, the hoop will have different kind of motions. Here we are investigating the jump, which will happen when the normal force is equal to 0. That is logically correct because when the hoop is jumping, there is no force that can be applied to the hoop by the ground. So the acceleration, vertical acceleration of point M will be equal to the mass point gravitational constant minus normal force. Because we don't have a normal force here, we can get these equation out of it. And if we consider the omega or the angular displacement will be around the center of gravity, it will be constant while the hoop is moving, while the hoop is jumping. So we can obtain a formula for the coordinate system x and y for the center of gravity. And it will start with the initial velocity, the time that's was showed with t, and the alpha is the same as the theta, which is the angle between the mass and the stable equilibrium state. So we can obtain an energy for this system. We can say that here, if we follow the equation, in the right part, in the right side, we can see the kinetic energy of the system, and in the left side is the potential energy. And if we follow this equation, it will give us one condition for the jump to occur in a minimal theta, which will give us the sine of half of the theta would be greater or equal to the equation we have on the right side, and which has the main parameters of initial velocity, gravitational constant, and radius of the hoop. Now, to see if the experiment matches our theory, I have some different masses applied to the system and different hoops, which are plastic hoop, metal, and wooden one, and 2 different types of ceramic, so we can see how does the friction or less friction will affect this phenomena. Now, as I said, the hoop is following a cycloid motion if we track only the hoop. But if we track the mass that is attached to it, it will follow a parabola shape. And the jump will happen when the parabola is outside the cycloid. And the theoretical framework, the GeoGebra simulation shows that too. Now, to see if our theory matches the experiment, this is the jump angle for the metal hoop, which is calculated with tracker 84.83 degree. And if we use the equation we had in the theoretical framework, we can see the theta will be equal to 85. The same equation and the theory match will go for the plastic hoop and the wooden one. So basically, it does match our theory with some error that was okay because of the problems we had with the problems we had in the experiment. Now we can see that how we can have a diagram that shows that what is the relation between the mass that is applied to the system with the angular displacement of the mass. So it will be a constant line. The angular displacement, as much as the angular displacement is increasing, the mass will stay the same. So, and another diagram that shows a linear relationship between angular displacement and the initial velocity. So we can say that as much as the initial velocity is increasing, the angular displacement or the theta of the mass will increase too. Now, to see where will the jumping motion happen, we have this ascending trend here for the relation between theta, the rotation angle, and the time diagram. We can see that the part that the diagram is increasing is where the jumping motion happens. And as I said, we will have a parabola shape if we follow the mass that is attached to the hoop, which can be seen in the left side. Now, to mention that I had the metal, plastic, and wooden hoop with different sizes and different masses applied to the system that they vary from 50 gram to 250 gram, and 2 types of ceramic. And one more time to mention that the hopping occurs, the parabola is outside of the cycloid. Now, if we want to see that how does the mass affect the hop size, we can say that when the for the metal hoop, as much as we are increasing the mass attached to the hoop, the hop size will increase too. The same thing happens for the plastic hoop and the wooden one. We can say the same ascending trend here. As much as we are increasing the mass, the hop size will increase too. Now, at the end for the conclusion, so we saw that as much as we are increasing the mass applied to the system, the hop size will increase too. And we know that there will be a limit for that. So the limit is when the mass is, we are increasing the mass, the inertia of the system is increasing too. So we will need more torque, so the hoop will keep on rolling. Now, this is a methodology of what we had in the phenomenon. And in conclusion, we had the comparison between the theory and experiment, and we saw that it matched. And these are my references, and thank you for your attention.
All right, thank you very much. I think we have some time for a question or two. I have a question about the angle. Was there any angle of jumping that was not allowed from your studies? Is there because what really surprised me is that one of your jump is very vertical. The first one, right?
It was 1 meter per second, but the hoop had a very great hop. I think it's because of the mass that is applied to the system. So for the one that I used in the video, it was a 150 gram that the mass was applied to it. But when we use a 50 gram mass on the same hoop, it won't have that much of a jump. So as I said, as much as we are increasing the mass, the hop will be more.
Yes.
It will be more. The hop will be more. The hop size will increase. Yeah.
Thank you again. All right, let's continue in this intimate setting, I must say. Filippos? Yes? All right, are you ready? What are you presenting today? The right spot. Okay, let's go. So are you on the Zoom already? No, you're not on the Zoom. So how are we going to do that? Yeah. Zoom should be on Discord. Do you have to are you on the Discord for IPT? No, no, it's fine. I can take your time. Don't worry. What's your It's in Greek, so I'm sorry. I don't okay. It's opening 500. Yeah. My full screen because there's a PowerPoint. Yeah. So I think this is working. We're going to have to close Python in the meantime. But okay, do you want to start and we'll close Python? I can do it when it's short.
So, hello, my name is Filippos, and I'm going to be presenting problem number 9, the bright spot. By shining coherent light on a spherical object, a bright spot appears in the middle of its shadow. That bright spot is called the Fresnel-Arago-Poisson spot due to the scientists that contributed to its understanding. When different types of solids, meaning differently shaped solids are hit by light, different patterns produce in the shadow region. The geometric connection between the diffraction pattern and the object illuminated by light is examined in this presentation. So the mathematics of diffraction show that the connection between the object illuminated by light and the diffraction pattern produced. The basis of diffraction is the Huygens-Fresnel principle. It states that every point on a wavefront acts as a secondary source of wavelets which mutually interfere, creating a new wavefront, and that process continues. Another really useful principle is Babinet's principle. It states that by subtracting the electric field of an aperture or an opening from the one of the undisturbed wavefront, we can get the electric field of the object illuminated by light. So we are focusing our studies in the Fresnel region because when someone refers to the geometric shadow of an object, typically refers to the near field diffraction. Besides that, it's more complex and beautiful. The electric field of the diffraction pattern in the Fresnel region is written in the form of an impulse response factor multiplied by a Fourier transform of the electric field of the opening or the block times a propagating factor. The geometry is hidden in the limits of integration, so it's neither apparent nor clear. The intensity is given by the complex conjugate of the electric field times the electric field. And that formula gives the whole diffraction pattern. But we are mainly focused in the shadow region. So shadow region is actually dependent only on the boundary radiations. McGill and Rubinovic showed that the electric field could be reduced from the 2D surface integral to a line integral with a low divergence theorem, which gives us a powerful insight. It gives us the insight that the boundary plays a really important role in diffraction, and that could probably lead to an approximation of 3D solids to their 2D projectional blocks. So here is a picture that we took when conducting the experiment in the University of Athens. We show here a metallic cylinder of small dimensions compared to a metallic sheet of the same dimensions. And the diffraction patterns appear to be pretty much the same. Another important thing about the line integral method is that it shows that the diffraction pattern of an n-sided regular polygon has n-fold rotational symmetry. So, for example, in the triangle, we have a 3-fold rotational symmetry. So both of the methods mentioned before hide the geometry in the limits of integration, but do not provide immediate insight to what the diffraction pattern is by just looking at an object. And this is where the evolute theory comes. The evolute of a curve is the locus of all its centers of curvature. When one signs an object of small curvature boundary changes, we can see that the predominant feature is the evolute of the object illuminated by light. The evolute of a circle is a single point, and it's the Poisson spot. So here's the evolute parameterization. X and Y capital are the evolute parameterization, then X and Y are the object's parameterization. And Let's start dealing with the experiment. The experiment was conducted in a dark room. We used a helium neon laser of 632.8 nanometers. We used a lens, a white wall with a smooth paper in order for the diffraction patterns to be clear, and a camera with a telescope lens. We also used various blocks and apertures. Most of the blocks were made out of paper. Some others were metallic. So starting with the beloved disk, we can write the electric field according to the Babinet's theory as the electric field of the undisturbed wavefront, and we're reducing from it the electric field from the aperture. This would give, if we calculate the intensity, it would write it in the form of alternating Lommel series, and the only near the center, it could be approximated by the zeroth Bessel function. So here we can see the pattern produced by a disk, the pattern produced by a sphere. The light on the outside is blurred. It's actually the same with the previous case. And the diffraction pattern produced by a cylinder. In the cylinder case, we can see some concentric luminous rings, but those would be seen in the other cases too. So the next shape that we examine is the rectangle. The rectangle, again, with the same process using the Fresnel approximation and the Babinet's theory, could be written in that form. And it gives us a pattern with many different stripes, and its angles are a little bit lighted. And here we can see a computer simulated diffraction pattern of a rectangle. So here the pattern is more apparent. The next shape is the ellipse. The ellipse is a really beautiful shape. Starting with small eccentricities, we get the Poisson spot, the Argot spot. When the eccentricity is increasing, we get a stretched asteroid, a Lamé curve, which is being stretched in the major axis. So that is the evolute of the ellipse. It's apparent that it's predominant. In small ellipses, the evolute is small. And in bigger ellipses, we can see not only the evolute being the stretched curve, but also some greater inner structure details. So the next case that we examine is the parabola. The parabola, as evolute, is a semi-cubical parabola. It's that lambda shape that appears in the shadow region. And here's a computer simulated diffraction pattern of a parabola. And here we can see the diffraction pattern that we took in the experiment we conducted. We can see not only the lambda shape, but also a second and a third line of the same shape. So it has also a greater inner structure. And here a parabola again. The next shape that we examine is the cardioid. The cardioid is expected to give an inverse cardioid evolute. So let's see if that is true. And apparently, also in the cardioid shape, we get the inverse cardioid evolute being predominant again. So here is the heart-shaped involute of a circle that is produced by unrolling thread from a cylinder, and its evolute is supposed to be the original cross-section of the cylinder from which it was produced. So we can see again that the evolute is a circle. For the conclusions, we show that in the near field diffraction, when we are considering the shadow region and normal incidence, we can approximate the small 3D objects by their 2D projection blocks. The evolute of the boundary appears to be bright in many cases of small curvature changes. For fast curvature changes, we can deal with those with the Fourier approximation and also with the line integral methods. And we conducted experiments for a variety of shapes. For a future work, it would be nice if we could apply this theory to more complicated shapes and show also that those shapes have a rotational, a fold symmetry too. So that was my presentation. Thank you.
Thank you very much. Do we have a question from the audience? Yes. Oh, you can go on.
Yes, not with the laser and the lenses, but with the obstacles, because most of those were made out of paper. So we cut the paper, and even a small symmetry change would lead to a big difference in the diffraction pattern. So we needed a really symmetric shape. So that was the biggest difficulty in conducting the experiment.
Okay, thank you again. Yes.
Is that fine? Yeah, there we go. Nice. So when I first explored the problem, I built a simulation, mind you, an actually physically accurate simulation with a good physics engine. And I just tried many different parameters, but what turned out is that almost all of them resulted in the same kinds of changes. If you get a Gaussian distribution, well, so still a Gaussian distribution, or by changing different parameters, it just becomes flattened like this, and eventually gets spikes at the edges where it is clipped. So we figured in an ideal Galton board, the choice of each of the binary choices has a 50-50 probability. And so there can't be any information carrying over from the previous peg. So by intuition, it's not unreasonable to assume that by changing the board from this idle state, you will carry on only some information from the previous pegs. And this appears to actually be correct. So by assuming that almost all information is lost on collision and only looking at the previous peg, we can make a simple model that is still accurate. So we will be considering only the probability that the ball continues traveling in the same direction as it did when it entered one of these units of 3 pegs. So all these parameters that you can vary usually result in the same kind of, this only affects this probability, but we will now be looking at the distance between the columns of pegs. And here we have a very large distance between the columns. And as we can see here, the ball comes flying in and it can't make the jump. So it bounces back the opposite direction it entered with. If we decrease the distance further, we increase the chance for it to actually be able to make this jump. So it moves faster, it's a shorter jump, and it continues traveling in the same direction. If we decrease it even further, we say get to this situation where the ball bounces back and forth and it loses all information and it falls straight down, and we get a 50-50 probability of going to the left or right. And as it turns out, many parameters only affect this probability. The bounciness, of course, affects how much energy it has. The spacing, as I just showed, peg shape can make it so they retain more energy. On and on, vibration just adds more randomness, making the memory less important. So, yeah, we decided to try to vary the spacing between the balls to try to create more interesting distributions. So what we did, we made this setup. We're looking at these 3 pegs. The rest of it's just to create a realistic range of randomness. And we've got this nice plot, all according to theory. So as we decrease the spacing, we have it's more and more probable that the ball continues traveling in the same direction up until a point where the ball instead starts bouncing back and forth, and so on. So by doing a regression here, we can see that we get a nice plot, a nice function to translate the probability for the ball to continue traveling in the same direction to a spacing between the pegs. So actually applying this, let me show what can be done. So here we have a nice just statistical simulation, a statistical model, assuming that this is how the Galton board works. So for 50-50 probability, here on the bottom, we can see the probability for the ball to continue traveling in the same direction. So now we have a 50-50, we get a nice Gaussian distribution. If we increase the probability for the balls to continue traveling, we instead get these spikes at the edges. If we make it very probable that they just bounce back and forth, we get these spikes. By having more interesting functions for this probability, say a polynomial function, we can get spikes moving back and forth like this. And we can even shift them left and right. And this is just for a really simple function. Here we can see a sine wave. It's kind of pretty, not very useful, but fun to look at, kind of satisfying. It's a fun shape. But of course, you're all wondering, is this model actually accurate? We're making lots of assumptions. Turns out it is actually pretty good if I chose the right window. Yeah, so here we can see the edges only distribution, and we can see it actually produces that kind of distribution. What we did was we generated a board and then printed the pegs, the dots on a piece of paper, and then thumbtacked pegs to a corkboard. And as we see, it actually works. We have some errors in the middle because, as we can see here, we never actually achieve 100% probability of continuing in the same direction. Another distribution, we can see we can get the balls to land in every other bin. Yeah. We also tried making a flat distribution. However, this didn't turn out quite as well as I had wished. But I do not think this is necessarily a failure in the model, but rather just human error. Assuming we only had an error in the model, we would have a symmetry over here. As we can see, some bins are receiving much fewer balls. So it's more likely that's just human error. And further studies have shown that these kind of distributions are very, very sensitive to small changes. Yeah, since the problem specifically asked about vibration, here we can see as we increase the frequency or the magnitude to like pretty much any value whatsoever, we get more and more normal distribution. starting with this distribution and applying vibration, we get this distribution. And this is just because with this model where the ball has probability of continuing or not, adding this randomness, it makes the information it carries on from the last row of pegs, it is dwarfed out by this random noise. And so we approach the 50-50 probability and we get the normal distribution. And yeah, we see we have a, I'll just skip this actually. Yeah, those are my main findings. So this is actually, it might seem too simple, but it's actually shown to work very well. And it allows for, it summarizes all kinds of effects in pretty much of both the vibration and many other parameters you can vary. And it all summarizes this in a single parameter, which is the probability of the ball continuing to travel in the same direction as it just did. And with this, it's a useful approximation. As we can see, we can actually create pretty much any distribution we'd like. And that's what I got for you tonight. So thank you.
That is a very elegant solution. Do we have a question?
Yeah, it's a mix of just doing things by hand, and it's a mix by just doing things by hand, and actually using a proper genetic algorithm. Which, since I have a nice physical accurate simulation, I could just do gradient descent, and I could just use a genetic algorithm to optimize the board for the target distribution, and then just print it and use in reality. Yeah.
All right. Thanks again. Oh, no, there's one. Yeah.
The simulation is not accurate to reality. It's only used to explore the phenomenon, but the engine is proven to, like, it has a large test suite for like constellation editing and that stuff. It's physically accurate, but it is not model of the setup. Currently, you have to measure the parameters for your current setup. But first, that is moving to, say, trying to figure out a way to measure this method parameter without running any experiments, just like measuring sizes or restitution. Yeah. I've looked at it from reality. The nice thing, since it's only more parameter, which summarizes many different other parameters, you can only like do this kind of box with just one page. Then you can generate reality and then try to work on it. But simulation has its own way of parameter. Okay.
All right. Thank you again. All right. Last presenter of the day, but not least. Super. Thanks for waiting all the way and being here.
Griffin. Oh.
You can just put it like
okay, yeah, for that. Or okay. We'll see. Yes, hear and see me. Great. Hi everyone. I'll end this conference with a presentation on the bright spot. So this problem is about having an object inside, for instance, a laser beam, and then seeing what happens with the shadow. And we typically get this sort of dot, which is unexpected with classical optics. But we're also to test this with different types of solids and see what we can extract for information. So a simple explanation of why we get a dot is that we have some incoming wavefront, and then the Huygens-Fresnel principle says that when it interacts with an edge, we will have like a Huygens source that is true like all the way up here. But we just look at the Huygens source that's spawned at the edges here, and that's going to have an interference pattern. And if we just follow those nodal lines, we'll get an increased intensity behind the object. And then it's interesting to, if we just look at the Fresnel sources arising from the edges here, we can sort of look at the three-dimensional case when we have tilted this entire thing. And then we can just set up a simple path difference, and based on that, calculate where we would get the spot on this screen. So in this case, we have y is basically how high up from the center line we get all of these spots. So if we change the angle here, we see that in the beginning we get quite different results. But when we propagate further, we see that we get exactly the same thing, even though we have the object at an angle, which means that even though we have some three-dimensional characteristic, we still get the same shape for long enough distances as we had without it. This, in combination with the fact that if we just look at the 2D shadow, we're also able to reconstruct a 3D object using various other algorithms. For instance, we can change the position of the light source, and we can rotate the object, or we can use some common machine learning algorithms to rebuild the 3D structure. We will only be concerning ourselves about the 2D structures of the objects we're looking at. So we also tried reproducing this with three-dimensional objects. Indeed, here we have everything to a screen, and then we take a photo at a slight angle. And it's very hard to see on these pictures, since it's very hard to find suitable three-dimensional objects that are small enough to reproduce the phenomena. But what we see is that we get a dot for both a cylinder and a sphere, which further supports this 3D to 2D reduction. We can also, since we know that the 3D properties aren't really that important, we can look further into the actual pattern or the projected shadow of the object and create a simple integral inspired by this path length difference we looked at earlier. And if you noticed, this is very similar to what the previous speaker talked about with, I don't remember the name of it now, but this integral has a name as well. We can also simulate this phenomena. So we will have an initial field, and we can sort of add a mask to it, which is the 2D shape we're looking at. And then using the Rayleigh-Sommerfeld integral, we can propagate this, this light onto a final plane using this integral. So for the experimental setup, we have primarily used the same as for the three-dimensional case, but here we have replaced it with a small plastic film where we have used an ink printer to print a wide variety of shapes. And then we look at the diffraction pattern, and we would have the same camera here. Then we have simulated basically the same thing. But here we have an initial field, we add our mask, and then we use the Rayleigh-Sommerfeld integral to propagate it down to a final diffraction pattern. So here's some comparisons from the experiment. And if we do a heart, a more interesting shape than just a circle, we can see 2 points coming up here. If we squint a little bit, we'll see these points in the simulation as well. But to amplify the effects of the inside, we can take the logarithm of the values, and we will see a very clear dot here, or like a heart-shaped behavior. And if we use this simplified model, indeed we see the dots arising at roughly the same place as well. We can look at more general patterns such as symmetry. So of course, a object with four-way symmetry is going to have a four-way symmetry in its diffraction pattern as well. But we can sort of look at different objects with the same amount of symmetry. And if we have star-like shapes, we see that it's all the edges that create the strongest diffraction patterns. But now the actual thing we're supposed to do in this problem is to basically reverse this integral. We've gone from this plane using this integral. Then the question is, can we go backwards? And indeed, we could do this with this integral, or basically reversing this integral, if we had the phase in this plane. Because in the problem, it's stated that this light has to be coherent here. So we know the phase in the initial plane, but we don't know it here. So we can use, this is a very well-studied phenomena, since you use this, for instance, in X-ray imaging. So we can just use all of these algorithms to reverse the integral, or rather getting the phase and then reversing the integral. So here's an example. This is more or less what's fed into the algorithm. And then we have used the algorithm, and it's able to trace out the contour. And if we compare this with the original shape, we see that the contour match exactly. So we're able to extract the exact measures of the object as well. Then we can have an even more complicated pattern. Of course, before you could see since we had the entire diffraction pattern, you can sort of guess from the shadow. But in this case, it's very hard to guess what the initial pattern was. But applying this algorithm, we're able to reverse it with very high precision. Indeed, this algorithm, we can look at how sensitive it is. So what we have fed into the algorithms each time is the entire diffraction plane, which would look like this. And then we're able to trace out it very well. But indeed, if we crop this and add a lot of shot noise, which would be the case if we have an actual photo, we still see that it, to a lesser extent, is able to reproduce the shape. So applying this to experimental data is not quite as successful. It's able to find the interior, but not really the exact radius. And for this shape, it's not super good. But this has a lot to do with the very poor resolution and angles and things like that of the data fed into the algorithms. So to conclude, we can get some information out of the dots themselves by comparing it to this simplified model we've constructed, where we get out the dots, but typically not the rest of the information. And if we allow ourselves to use the entire diffraction pattern, we can use, for instance, this hybrid input-output error reduction algorithm from the literature to reverse it with extremely high precision. So this is the software used, and thank you for listening.
Nice. I feel that this is very complementary with the previous presentation that we had, because